We'll do the another one. Yesterday we have considered
Yes, sir.
one problem, first problem, that is problem for pyramid connection. Pyramid connection we have considered. Now we will consider any doubts in the pyramid connection. Previous problem. So if there are no doubts, then we can go to the second one, design of unstiffened seated connection. So here a little bit procedure is there. This one. Sorry, join here, sir. Join. We'll go to the design of unstiffened seated connections. So unstiffened seated connections will have seat angle and cleat angle. The below one is the seat angle where the beam rests. You can see the diagram. Seat angle, it consists of seat angle and cleat angle. This is the seat angle. Seat angle, this one, where the beam is going to rest to transfer the load, shear force, that is through this seat angle. And this one, the top, on the top of the beam, cleat angle will be there. So this is the column. Left one vertical member is the column. So cleat angle is connected to flange of the column and flange of the beam. And the seat angle is connected to the flange of the column and the bottom flange of the beam. So on this seat angle, the beam will rest, and we have to make the design the connections. So we have to make the design the connections. This one, size of the bolts and the size of the seat angle and the cleat angles. So all this we'll consider in the today's problem. We'll consider one problem. Design of unstiffened seated connection. So procedure, small procedure is there for this one. So in this seated connections, seat angle is casted to the seat angle is bolted in the shaft. That is, the seat angle will be connected to the column in the shaft by means of bolts, and then the beam and the seat angle and cleat angle will be connected in the field. That is the procedure in this one. And the first step is you have to calculate the shear force. That is the end reaction to be transmitted to the column through the outstanding leg of the seat angle over over a length of b, small b, and the b is calculated using this formula, capital B minus root 3 H2, where b is given by the shear force Fp, a permissible bearing stress in the member, and thickness of the web of the beam. Tw is the thickness of the web of the beam, and F is the shear force at working load that we have to consider. So Fp is 0.75 times the Fi yield stress of the metal, and H2 is there here. This one H2 will come. So H2 is the thickness of the flange plus radius, root radius of the beam. This we will consider this. So next, select a trial section for the seat angle. It consists of an angle like this. So this is the UDL through the beam that is coming on the projected outstanding leg, and this vertical leg is connected to the column, flange of the column. Select a trial section for the seat angle. Provide a clearance of 10 mm between the beam and column. So 10 mm gap will be there. This is the column. So from the column face, flange of the column, 10 mm gap will be there. Compute the distance of the end reaction from the critical section, where the end root fillet weld H2 from the extreme fiber of the flange. So H2 will be, this is the root and this is the flange thickness of the leg that is connected to the flange of the column. So H2 is given by thickness of the flange, this one, thickness of the flange, and R1 is the radius. So here the critical section will be there, that is considered as XX. So this is the section we will consider for calculation of the bending moment of this one. So calculate the bending moment at the critical section XX. This one. Small b is the outstanding leg minus 10 mm will be considered here. So 10 mm gap will be there here. We have to consider. So then assume the length of the sheet angle equal to the width of the flange. So length of the sheet angle is nothing but perpendicular to the plane of the paper. So perpendicular to the plane of the paper, that will be the length of the sheet angle, that will be equal to width of the flange of the beam. So perpendicular to the plane of the paper, the sheet angle length, so that will be equal to the, so full bottom flange of the beam will rest on that one. So here it will rest for a length of b. Compute the moment of resistance of the sheet angle, which should be greater than the bending moment. So you have to calculate the bending moment at the critical section XX here. So it should be greater than the, your design moment should be greater than the occurring bending moment. That is the criteria for the bending moment. So next is the sheet angle is connected to the column, that is tension in the workshop, and find the number of bolts required for that one. So design of the bolts, that is shearing and bearing will be considered. At least one will be considered for the required number of bolts. Then connect this cleat angle, that is the top, that is occurring on the angle occurring on the top of the beam, on the top by 2 bolts on either leg. So on the top, that will consider doing the problem. The diameter of the bolt should be equal to the diameter. The diameter of the bolt should be equal to the diameter of the bolts used to the connecting the sheet angle. So whatever the diameter that we will consider for the sheet angle, the same diameter bolt should be considered for the cleat angle also. So this is the sheet angle. So whatever the diameter of the bolts we are considering to connect this leg to the column, the same diameter bolt should be used for cleat angle also. That is the cleat angle coming on the top of the beam, that is connecting the flange of the top flange of the beam to the flange of the column. So if you refer the diagram here, connection, well, bolted connection. So this is the sheet angle here at the bottom of the beam. So whatever the diameter of the bolts it is required, you are designing for the shear here. The same diameter bolt should be considered for cleat angles. Here on the bottom of this one also, bottom of the beam, outstanding leg. So we will consider one problem, a simple one. This is also. So in ISMB, Indian Standard Medium Beam, 450 is nothing but the depth of the beam. ISMB is to be connected to the flange of the column. ISHB, Indian Standard Heavy Beam. This is also I section. Depth is 300 mm, but the weight is 618 Newton per meter. The end reaction transmitted by the beam is 120. This is the shear force to be transmitted. Design an unstiffened seated connection. Use 20 M20 block bolt. So that is the diameter of the bolt is 20. It is given. If it is not given, you can assume. So first step is the shear force to be transmitted to ISMB 450. That is the beam. The properties of the cross section, thickness of the web. You refer the steel table. You are having the steel level. You refer the thickness of the web of that ISMB 450 mm depth is 9.4 mm, and thickness of the flange is 17.4 mm. So H2, that is thickness of the flange plus radius at the root. So R1 is the radius connecting the web of the beam to the flange of the beam. These values will be available in the steel table. You can refer that one. That is going to give 32.4. Now we calculate the B. B is given by the formula F by Fp TW. So F is the shear force. It is 120 kilonewton. Fp, that is 0.75 times the Fy, yield stress of the material, 250 Newton per mm square, multiplied by 0.75. Then thickness of the web. Thickness of the web is 9.4 mm. So you will find B value equal to 68.094, but minimum should be considered. Another for small b, the formula is b minus root 3 h2. H2 is this one, 32.4. So b minus 32 root 3 into 32.4. If you consider this value should be at least equal to b by 2. B by 2 is 68.09 by 2. So if we calculate this one, subjected to a minimum 34.5. So you are getting for this from this formula it is 11.96. So you should consider b equal to IL, minimum value of 34.5 mm. So b is 34.5 mm. So you refer the figure 8.9, this one. So this one, b value 34.5. That is the length of the force, that is shear force, length of the shear force here on this outstanding leg, 34.5. So this one, b small b value is 34.5. Now we will try with Indian standard angle of size 150 by 115. One leg is 150 mm, other leg is 115 mm, thickness is 12 mm. The root radius, you can get this one steel tables 11 mm. Critical section you have to consider. Critical section is T plus R1, thickness of the flange, it is 12 mm here, and radius of this Indian standard angle R1 value from the steel tables you have to consider. This is going to give 23 mm from back of the angle. So that is thickness of the flange plus yeah, this one. This is the thickness of the flange, the root radius, this one. This add these two values, it is going to give uh, T plus thickness of the flange plus root radius, that is 23 mm from the back of the angle, this one. Now center of gravity. So that is a 10 mm gap plus b by 2, small b by 2. Small b by 2 I have calculated 34.5. So this is the center of gravity. This one. Now you consider the factored shear force. So partial safety factor 1.5. This is the occurring service shear force 120 kilonewton. So the force into distance will give the moment at the critical section. So this is 1.5 into 120. This is the force. And the eccentricity of that force 27.5 minus this 23, the distance to the critical section, this one. So the moment is 765 kilonewton millimeter, this one. Now length of the seat angle, that is length of the seat angle is perpendicular to the plane of the paper. So that should be equal to the width of the flange of the beam, because the entire flange should rest on the seat angle, length of the seat angle. So that is 150 mm. Width of the flange of the beam is 150 mm. So the length of the seat angle should be considered as 150 mm. So that full support will be there for flange of the beam. That is perpendicular to the plane of the paper is 150 mm. Now you consider the plastic moment capacity. Plastic moment capacity, you know the formula MP. MP equal to plastic section modulus into Fi. So for the rectangular section, that is the outstanding leg. This is, we consider the outstanding leg. This is the B and thickness of this one angle, outstanding leg angle thickness, and this is the B value that we have calculated. So BT square by 4 is the ZP value. This you have already considered for beams. This one formula NP plastic moment capacity BT square by 4 into Fi. So the same thing is considered BT square by 4 into, that is ZP into Fi, divided by partial safety factor, this one 1.25. So we'll get the design moment capacity here, this one. So this is the plastic moment capacity. Fy into Zp is the plastic moment, and if you consider partial safety factor in the denominator, we'll get the design moment capacity. So this is the design moment capacity in terms of unknown thickness. What is the thickness required, that we will calculate. Thickness of the sheet angle, this one. So you equate that 7,500 T squared to the uh, occurring moment. So occurring moment 765. This you have calculated here. 765 into 10 power 3 Newton millimeter. So from this equality, find out the T value, required thickness. So required thickness is 10.099 mm. So you consider a higher value. 11 will not be available. So you consider 12 mm inner strand angle. The size of the angle is now thickness is 12 mm. We are considering so that is sufficient. 12 mm thickness is sufficient. If the thickness requirement is more, you have to redesign this one. The requirement of thickness is more. So that is if you get more than 12 mm here, then you have to redesign this one. Now, once you got the size of the seat angle, now we design for the bolts resisting the shear in shear and occurring shear force in single shear and bearing. So for the single shear, this one because the seat angle is connected to the flange of the column. So that will be single shear. So this is the area Fu by root 3 into partial safety factor and root is in this shear we are considering. So multiplied by 0.78. So this will give the strength of the bolt, single bolt in a single shear is 45 kilonewtons, 45 kilonewtons. So generally bearing value will be more for the bolt when compared to the shear value. So you consider the number of bolts required, that is total occurring shear force, factor shear force divided by the shear capacity of single bolt. It requires about 3.97. You round it to 4 number of bolts. So 4 number of bolts is nothing but in a row 2 bolts will get. So total will be 4. So that is yeah. So this is one bolt on the back of this one. Another bolt will be there. Here is one bolt on the back of this one is another bolt. So 4 bolts will be there here. So connecting this seat angle to the flange of the column. This one. So size is 150 by 115 by 12 mm. So 4 bolts are required. Now ISA 150 by 115 by 12 mm thick angle. So 2 rows of bolts can be provided. Now, so this is related to seat angle. Now connect the top cleat angle. So this top one. So the same size diameter bolts. So two numbers. One is connecting the flange of the column. Another one is here. Both sides of the web. Here also 2 bolts on both sides of the web. Same diameter, M20 diameter. 20 diameter, 20 mm diameter bolts. So this is the design. Same thing is considered for outstanding leg of the seat angle here. 2 bolts will be there. One on this face and back side, another on the back side of this web of the beam, another bolt will be there. So this is the design of unstiffened seated connection. Is it okay now? Is there any clarification required for that? You have to draw the diagram also in the examination. Is it okay? So first what you have done here, you have considered the details of the beam. And H2 value is calculated, capital B is calculated and small b is also calculated. And then afterwards, you have chosen seat angle. So critical section location you have calculated and center of gravity of the load is also calculated. Then factored shear force is calculated. Then factored moment is calculated. Now factored moment is equated to the plastic moment, design moment capacity of the beam. So that is design moment capacity of the seat angle. So equating that, you will get required thickness. The required thickness should be less than the assumed one. You have assumed 12. So required thickness is only around 10.099 mm. So that will be 12 mm will be sufficient. So now we design the bolts in shear, single shear. Bearing is also calculated, you have to, but bearing strength is more than the shear strength. So this value, shear value is considered to calculate the number of bolts required for connecting the seat angle to the flange of the column. Then you consider minimum number of bolts, 2 numbers for the vertical leg of the cleat angle, 2 numbers for the horizontal leg of the cleat angle connecting the column and beam, and again 2 numbers connecting the beam to the seat angle, one on this side and another on the back side of the road. Is it okay now?